All right, so it is April 6th. We're doing our warm-ups. I was a little late on hitting the record button this time, but so we went through one example over here, derivative of arc sine of 2x plus 5, and now we're really quickly going to do this one on the right-hand side where we're going to take the derivative of arc sine of e to the 2x. So I picked this one on the right-hand side because this is an example of multiple chain rules. So what I want you to observe with this one is here we have this outside function is arc sine, and then we have an inside function which is e to the x, and then we have another inside function which is 2x, right? So there's sort of three layers of this one that we have to unpeel. And so each time that we're going to go through chain rule, we're going to think about, hey, what's our next inside function? What's our next inside function? And we're going to keep multiplying by those derivatives. Okay, so the first pass through this one, we would get 1 over the square root of 1 minus e to the 2x squared. Okay, and so what we have to do is I have to multiply this by the derivative of my inside function. Okay, so I'm going to multiply by the derivative of e to the 2x. Okay, so I'm going to go ahead and shift this over. Sorry about this. We've got some whiteboard issues here. Okay, so we got more space now. All right, so derivative of e to the 2x, I'm going to need to multiply by this derivative. So I'm going to go ahead and replace that. So the derivative of e to the 2x, I'm going to use chain rule on that again. And so what we're going to get is we'll get e to the 2x, and I have to multiply that by the derivative of 2x. That's my third inside function, right? The third piece of this. And so this derivative, the derivative of 2x, just becomes 2. Okay, so going through this, right? So this is the derivative of my outermost function, and then we have the next level, and then we have that final level in there. Right, so my apologies on the shifting of that whiteboard in the background, but how does this feel? We feel okay about these? Molly's good. Good. Bunch of thumbs up. Excellent. Okay, so derivative of arc sine is what we focused on last time, and today we want to think about the derivative of arc tangent. Okay, so very similar to what we did last time, we're going to go through and we're going to see if we can develop this. So if we remember on Friday, I sort of went through everything. Today I'm hoping we can make this a little bit more interactive. There's not, so we've got 7 here, so it's not too big, but let's see if we can all work through this together. And so if you are following along in the book, what we're going to do is this is activity 2.6.3. Okay, so it's a guided activity where we are all together, we're going to derive what is the derivative of arc tangent. Okay, so when I look at this, this is our goal, is to develop this rule. What is the derivative of arc tangent? Okay, and so to start, right, so if we work through this, part A of this says, hey, let r of x equal arc tangent, and we are going to use our inverse knowledge to rewrite this. Okay. All right. So if we go back, if we remember what we did on Friday, what was step 1 here? Does anybody want to chime in and I mean, what did we do? All right. So 2.6.3 says, use the relationship between arctangent and tangent to rewrite this using only tangent. So I want to rewrite this saying, instead of having an arctangent in there, I just want to have tangent. So any ideas? All right, so give me, yeah, okay. So x, yeah, right, if what Emily puts in the chat, if y equals arctangent of x, then x equals tangent of y. So instead of y here, we're gonna have r of x, okay? So what we can do is we can rewrite this as tangent of r of x equals x. Okay, so for part A, this is what we want to do. Okay, so tangent of r of x is equal to x. All right, so part B says differentiate both sides of the equation you found in A and solve for r prime. Okay, so what we want to do is take this, we're going to take the derivative of both sides, and then what should happen is we should find that r prime pops out of this. Remember, like we did last time, right? So the derivative of r of x is the same as arctan, and so we're going to see an r prime come out of this, and that, whatever we can simplify that to, that's going to give us the derivative of arctangent. Okay, so so for part B, what we're going to do is take the derivative of both sides. On the right-hand side, derivative of x is just 1. On the left, the derivative of tangent is secant squared. Okay, so we get secant squared, and then we leave our inside function there, and then we're going to use chain rule and multiply by r prime of x. And so what we're asked to do is solve this for r prime, and so we get r prime of x is equal to 1 over secant squared of r of x. Okay, everybody following along so far? So we are, again, we're doing activity 2.6.3 here from the book, and we've gone through parts A and B. Right, and so now we're saying part C says, recall that r of x is arctangent, so we're going to replace this in here, right? So we get our derivative, r prime of x, is 1 over secant squared of arctan of x. Okay, let's see if I can do this again. Right, so just giving ourselves a little bit more space here, right? So, all right, so part C, r prime of x is 1 over secant squared of arctangent. So up to this point, I think we're probably okay, but then when we get to part D, this is typically the harder piece here. Okay, so what I want everybody to do is start to think about this. I want you to introduce your right triangle, and remember that arctangent is an angle. Okay, so arctangent is an angle, and we're gonna have a right triangle, and then we're gonna put our little angle theta down here, and we're gonna say theta is arctangent of x. So what we want to do is, this is the angle that we have to plug into tangent. Okay, this is the angle we have to plug into tangent to get, right, to get x. So think about the three sides of the triangle, and what is tangent? Tangent is opposite over adjacent. So what do the sides of the triangle have to be? So what do the sides of the triangle have to be? Yeah, all right. So we're gonna put values on the sides that aren't the hypotenuse, right? So we're gonna put a number over here in this green blob, and we're gonna put another number down here on the bottom. Okay. And so what we want, right? So the green is our opposite. So what we want to do is we want to come up with an expression such that whatever we put in the green divided by whatever we put in the blue, okay? We want this to be all equal to x. Okay, so that would mean tangent of theta is equal to x. So we have to think about, we can put any numbers that we want or any expressions that we want, but I want green over blue to be x. And it's pretty helpful to just pick the simplest possible solution here. So if you had to pick values for the green and the blue so that when you do that division you get x, like what would be the easiest thing to do? Any ideas? So they're not going to be numbers, so it's going to be expressions, right? So you can use x if that makes sense. So it could be, you could pick numbers, but what you want is you want the result of this to be x. So you want to pick, right? So you want to pick something for green and something for blue, so that when you simplify, the result is just x. Right. So you could say x squared over x, right? But you could also say x over one. Yeah. Yeah. So x over one, I think, would be the easiest thing. Are you all seeing my board update? No. Yeah. So yeah, I don't know. It's updating on my iPad. It's not updating here though. So let me try to reshare here. Better? Yeah. So Bella says x over one, right? So funnily enough, yeah. So you would say like, yeah, what's the simplest thing? You could make this x over one, so that if I do tangent of theta, I would get x divided by one, and so this is the appropriate value for theta. Okay. So what we want to do now is, so I'm going to clean this up a bit. So now what I need to figure out what value goes up here in this triangle. So we can use Pythagorean theorem to say, hey, I know, once I know two sides of this triangle, I can figure out what the third side of the triangle is. So Riley, when you say tangent of x is r of x, what do you mean by that? we're thinking here. So what we're looking for is a value that would go up here. That's okay. No problem. So any ideas what would go up? What would go up here? We have Pythagorean theorem tells us that 1 squared plus x squared is equal to, right, whatever this value is, c. Yeah, exactly, right, square root of x squared plus 1, right? So this would be 1 squared plus x squared equals c squared. And so if I take the square root of both sides, what Molly said here was, yeah, you'd get the square root of x squared plus 1. Okay, so that's what we're going to do. We'll go ahead and put that up here. Okay, so we'll get rid of this stuff, and then we'll say, hey, this is the square root of 1 plus x squared. Okay. All right, so so what we're looking for now is I can think about this as r prime is 1 over secant squared of theta. Okay, so 1 over secant squared of theta. So the question is, all right, well, what can I do, right? What can I do to simplify this? So now I need to think about what is secant squared. So if we go back to our activity, the activity says, in terms of x and 1, what is the value of cosine of arctangent of x? Okay, so in part E here, it's asking us, hey, effectively, what is cosine of theta? So why do I care about cosine of theta? There's no cosines in here. Yeah, 1 over, yeah, exactly. Secant is the inverse of cosine. So we're picking up some steam here. So where is this going? Where's the end result gonna be? Yeah, let's get rid of secant, right? So give ourselves some more space here. Sorry about the jumping around. So yeah, let's get rid of the secant, right? So this ends up being 1 over, right? 1 over cosine squared theta. Which ends up just being cosine squared theta. Right? All right, so again, when we're looking up here, we're sort of tracking our derivative that we want up here in yellow, and it turns out that if I can just figure out what cosine of theta is, then cosine squared theta is what I want. So we got rid of secant, and then so we have a suggestion. Cosine is 1 over the square root of x squared plus 1. Okay, so cosine is adjacent over hypotenuse. That's right. So we're moving here. So we're going to go ahead and erase this. So cosine of theta is 1 over the square root of 1 plus x squared, right? So this is, if you're thinking about this in terms of trigonometry, this is my adjacent side divided by my hypotenuse. Okay, so you've got like a SOHCAHTOA thing going on here. Okay, so finally, what we can say is r prime down here on the bottom, right? So this is part F. R prime from above we said was cosine squared of theta, which ends up being 1 over the square root of 1 plus x squared. All of that is squared. Okay, so we took our cosine of theta from above. Let's do red highlighter. Okay, so we took this and then we plugged it in for our cosine, and then this squared right here is this squared over here. And so when it all comes out in the wash, we get 1 over 1 plus x squared. Okay. So this is, I think, a pretty awesome thing. Again, I get pretty excited about this one. I like to derive inverse sine. I think that's a cool thing. And also, I think this one is pretty cool how everything just sort of works out really nicely. We had this crazy function arctangent that we brought in as the inverse of the tangent function. And then when you take its derivative, the thing that comes out of it is just this really nice expression right here, right? So there's no trigonometry in this. There's just just an x. So to me, that is really pretty cool. Okay, so all of our work, I mean, despite our troubles with the virtual Blackboard, but we have all of our work here and sort of all of our steps as we went through them. So on the next slide, let's go ahead and let's just write a summary, right? So our derivative of arctangent, right? So we can put this one in our rules is 1 over 1 plus x squared. So that's pretty cool to me. I like this one. All right, so arctangent is super useful. We use it a lot when we do when we're finding angles and when we are doing some digital animation stuff. Okay, so what I'd like to do now, we've got about half an hour, a little less than half an hour left, 25 minutes. So we're going to go through activity 2.6.4. I already did part B the other day. So I'll try to do part A, and then I'll split us off, and then maybe we can take a few minutes to think through C, D, E, and F, and then we'll come back together. Okay, so just to set us up with this, part A is asking, let's find the derivative of this function, x cubed arctan plus e to the x times natural log of x. Okay, so when I look at this, we're gonna have multiple rules. We'll see if we can put them together. Okay, so again, we're gonna take the derivative of this. All right, so what do you all see when you look at this? I mean, we see that arctan in there, right? So that's our new function, but yeah, I see product rule, right? So e to the x times natural log of x. Ah, so Luke, you're saying that this thing right here simplifies to be 1? Okay, so you're close. So it doesn't in this case, So if we had them composed, so if we had e to the natural log of x or natural log of e to the x, okay? In either case, these would simplify to be x because they're inverse functions, but that only works when you compose the two functions together. So in this case right here, we're not using function composition, we're multiplying them. So that this property is not going to apply. So we're not going to have that. Okay. That's a good thing. It's a good thing to observe, right? Because we do have this special property of e and natural log that they do cancel each other out sometimes. Okay, so let's go ahead and we'll back this up. All right, so what I do, I see product rule. So we're going to go ahead and run with that, right? So I see product rule because there's really a multiplication sign right here. And we have this multiplication sign right here. So what we're going to do is we're going to go through and we're going to have two product rules. And so we'll start out with the first one is x cubed times arctangent of x. And so we'll go ahead and set up our product rule for the first part of this. Okay, so let's go ahead and denote this with a color. Okay, so this is going to be my green part here. Okay, so my first function is x cubed, so I'm going to leave that alone. I'm going to have to multiply in the second spot by the derivative of arctangent, which we just saw was 1 over 1 plus x squared. So first times the derivative of the second function, and then I have to do it the other way around, right? So this one, in this part over here, I leave arctangent alone. I have to multiply by the derivative of x cubed, which is 3x squared. Okay, now I'm just going to write on a new line here. We're going to have to do the same thing for the next piece, right? So what I'll do is I'll set up my product rule framework here, and then in each of these pieces, we're going to go ahead and put in, right? So this is our blue piece. We're going to put in each spot. So e to the x is left alone. Then I have to multiply by the derivative of natural log, which is 1 over x, plus then I'm going to go do it the other way around. So I leave natural log alone, and I have to multiply by the derivative of e to the x, but the derivative of e to the x is just e to the x. Okay, so when I put all this together, this is the full derivative, right? So it's pretty long, so we broke it up into 2 lines. But this all together is our derivative. Okay. So we did B. So this is 2.6.4a. And so let's go ahead. Is the derivative of natural log of x always 1 over x? Yes, it is. So the only time that you get an additional piece to that is when the base is different, right? So if you have log base 2, it would be different. But yeah, this one is, yeah. Okay, so we've got 1, 2, 3, 4, 5, 6, 7. So I'm going to put us into 2 breakout rooms so you all can chat a little bit. Let's see if we can do C, D, E, F. Let's see how far we can get. Okay, so let's go ahead and do some breakout rooms. Okay, so we've got 4 and 3. So I'm going to go ahead and open them up now.
He said CD.
Hello.
Hi.
So how is that? This is okay so far?
Yeah, pretty good.
All right.
That's a lot. I don't think I'll get them all done in like 10 minutes though.
But that's okay. I mean, I think one of the things that I'm realizing is, yeah, for the distance learning, we're going to move at a slower pace. You know, things just sort of take a little bit longer when you're not sitting next to people.
Mm-hmm.
But that's okay. So we're thinking about part C right now?
Yeah.
So do we have any questions or?
I think I'm good
Yeah,
for
pretty
now.
good.
Yeah, I'm good right now.
All right. So I'm going to go jump in the other breakout room and see how they're doing.
2.6.4. It's right over the header for it.
Hello.
Hello.
All right. So how are we doing? We're getting set up here.
Yeah, we're just finding the stuff in the textbook.
Yeah. So we're in section, so derivatives of inverse functions on the left sidebar, and then it's like 3/4 of the way down, right?
The one that you just did was A, right?
Yep. And when we did B on Friday.
So just do C, D, E, F.
C, yeah, we'll start with C and see
Okay.
how we're doing.
Can we just leave A in that form, or do we have to simplify it at all?
So you don't have to simplify it. No, I think that's a fine form. So the general rule that I give to people is, you know, we don't have to simplify it always. It just depends on what we want to do with it. So if your goal is to just put it into WebWork, then I wouldn't simplify it. I think WebWork will take the unsimplified answers. Sometimes what we're going to want to do is take another derivative. So if we're asked to find the second derivative, so if I gave you that function and said, hey, let's find the second derivative, it might be beneficial in a lot of those cases to simplify. So it just depends on what you want to do. And the most common thing is if you're going to take a second derivative, you probably should simplify. It's going to make your life a little bit easier.
Okay, I just wanted to check.
So with C, would you start off by doing the derivative of, like, would you put 27 on the outside of the parentheses, and then, like, I don't know, would that be like the first chain rule, and then the other chain rules are inside that?
That's right. Yep.
Okay. It's a lot of chain rules in there.
There are a lot of chain rules in there. One, yeah. So let's go ahead. So I'll bring up a Desmos share so we can try out something like this. So remember, if you want to, right? So I'm going to go ahead and click off our grid. So since I'm controlling this, I can typeset over here, and then if you all want, you can annotate over in this area. Okay, so this is our function, right? So arcsine of 5z plus arctan of 4 minus z all to the 27th power, right? So you get arctan of 5z.
It was arcsine.
This was arcsine, right? Arctan of 4 minus z.
Yeah.
And then all of this is raised to the 27th power, okay? So we're not going to worry about the error messages it throws us because we're just using it to typeset here. All right, so you're saying this is 27 times something raised to the 26th power, something like that?
Yeah.
And so what would you put in here?
I'm guessing the original function there, the whole thing, yeah.
Yeah, this whole thing, right? And then what we're going to have to do is we're going to have to multiply by
the derivative of the inside.
Yeah, right. So the derivative of
which would just be two more chain rules.
That's right. So as we go through this, we're going to have to use chain rule on this one, and we're going to have to use chain rule on this one.
All right.
That's ugly.
It's ugly, yeah, right.
So wait, would that just be like, because that would split up into the derivative of arcsine times 5z and then times the derivative of 5z. So would that just be a bunch of different multiplications in a row, or would you have to figure out, like, put it in a different set of parentheses kind of thing? I don't know.
No, so this all would go in one set of parentheses like this. And so what you're saying is you would take the derivative of arcsine, which is 1 over square root of 1 minus something squared, right?
Yeah,
And then you said times the
times 5.
times 5. And so what would go down here?
5z, yeah.
Right, so this is the derivative of arcsine. You're plugging in 5z here, multiplied by the derivative of 5. Okay. So what would go over here?
Oh, and then this plus sign is what's okay. So then that would be 1 over 1 plus x squared, which would be 5z squared.
Not 5z.
Not 5z. Oh, 4 minus z.
Right.
Yeah. And then it would be minus 1 times negative 1.
Yep. And so this would be your derivative. And so Riley, yeah, this one is pretty ugly, yeah.
Pretty nasty, yeah.
Yeah. So a bunch of chain rules, right? And then but then we're seeing the arcsine coming there and the arctan. So again, right, but this was great. So Caleb, you did a great job sort of dictating through this. And then you're just sort of picking out the different pieces. When to use chain rule, what's your inside and outside functions. That was good.
So can we leave it just like that, or is there any way you want us to simplify that more? Like, would you
I would just leave it like
27 or no?
that. No, I would just leave it like that.
Okay.
So if we get to this point, that's good enough, and WebWork will take that.
Okay.
Okay.
Yep.
So I don't know if one of you wants to, if this is helpful for you, if you want to sort of take over the Desmos thing, or if talking through it is good. Yeah, this was good. And so we'll go ahead. I'm going to jump in with the other group, see how they're doing, and maybe I'll come back there. Okay, so I need to stop my share here. Yeah, let's go ahead and join the other one. All right, I'm back. Seems like everybody's muted. Are we
Hello.
chatting with each other here?
Yeah, we just kind of talked about what we got for C, but I'm doing D right now, so.
Okay, so
Yeah,
I just went,
started D.
yeah, I went through C with the other room. So let me share my screen here. So did you all get something that looked like this?
Yeah.
Yeah.
Yeah. Oh, I forgot the second. I forgot the 5 and the -1. I always forget that.
This was your site. This right here is what you're talking about?
Yeah.
Yeah, so remember when we take this derivative, you're gonna have to, there's gonna be another chain rule there. So you've got the
Yeah.
first chain rule, and then this would be a second chain rule.
I always forget that in WebWork too. I'm like, what the heck? That's right. And then I look over and I'm like, oh, I forgot that again.
You're not alone. You're not alone. So, all right, so there's part C, and then here's part, right, so here's part D. All right, so part D, we're bringing up cotangent of arctangent of Y is our expression. What do you got for me? What are you thinking about?
Mm,
So you're saying chain in a product. So I see the chain, I see the composition. Where's the product, Luke?
The cotangent times the arctan.
So
Or,
this is
oh, is that? Oh,
it's of
okay, yeah.
so we're
So
plugging.
is it like? Is it a double chain?
So it's not double chain. There's only a single chain rule here, right? So your outside function is going to be cotangent, and then your inside function is arctan. So there's just one chain rule here.
I got it.
Negative cosecant squared of arctan of y times 1 over 1 plus y squared. Yep. So something like this, Bella. So you got your outside function, right? So negative cosecant squared. That's the derivative of cotangent. And this is going to have to go in here. And we're going to end up multiplying by the derivative of our inside function, right? So as we're breaking it down, we have something like this. And then the derivative of our tangent is exactly what Bella said here, right? So we want, this should be, right, 1 over 1 plus y squared. Yep. All right, so Bella, it seems like that was good for you. Everybody else so far so good? This one makes sense? All right, so I'm gonna go check in with the other group for 1 minute, and then I'll bring us all back together to wrap up.
Over y squared.
One over y squared.
How would you get 1 over y squared from that?
This. So what you have here is almost right.
What am I missing?
You just got this extra y here.
See, that's what we were just talking about. I don't. So it would just be, okay, yeah, I understand now.
Yeah, so this is, if you just got rid of that y, then that's good. Yeah. So this is, so you've got the derivative of cotangent is here, right? And then this is your inside function, and then you're multiplying by, this is the derivative, right? So this is the derivative of arctangent. So this is right.
How did it, so sometimes I'll like try to help myself and use this website here.
Yeah, so there's lots of derivative calculators. So one of the problems is they simplify, right? So what's happening with this derivative calculator is they're going to simplify in the background. Their simplification is going to be super, super duper simplified. Okay, so if we go back to our answer, there's probably a way where we could combine this, right? So using some crazy simplifications, there's probably a way that we could rewrite this in a more simplified way.
Yeah.
What the derivative calculator is doing is it's making all of these simplifications that, at least from my perspective, regular humans don't simplify that way.
Yeah.
And so, again, I mean, if our goal is to get the answer, those derivative calculators are great. I don't think there's anything wrong with them. When what you're doing, you're asking the questions like, hey, this is weird. So that's exactly what you should be doing. But the answer is, most likely they simplified this expression using some trig identities that, maybe we're not using or we're not thinking about. And so your answers may not always match up.
All right.
But yeah, so that's, I mean, it's good to check, but just keep that in mind that if it doesn't match up, it could be that there's a weird simplification. So just, I mean, if you're ever wondering, you know, if it's right or wrong, you could always run it by me and I can take a look at it.
Or you could just plug it into Desmos and see if they're the same thing.
That's right. So you could graph this and you could graph that. But remember what I would do before I graphed it is I would change all of these to X's. Okay. So
Yeah.
just the way Desmos.
Yeah.
So it would be like, I would graph it with this as an X. I would graph it with this as an X.
Yeah.
And the X in the first one too. Arctan X instead of arctan Y.
That's right. So you would replace all your variables with X's, and then that's going to make your graph over here work out better than with Y's. Okay. All right. So we're close to out of time here. So what I'm going to do is I'm going to close the breakout rooms and bring us back together, just so we can wrap this up. All right, so we're 1 minute over here, but I just want to put some closing remarks out there. So it seems like we did some good work here today, and we figured out some stuff as we're going along. As we're talking through it, it seems like people are putting the pieces together. So I thought it was a good session today. One thing that came up in one of the breakout rooms was sort of when we check our work with the online derivative calculators. Sometimes they don't always match up. So we talked about how, sometimes those derivative calculators will do simplifying, and their simplifications aren't always obvious as to what they're doing. And so if you're doing that, so when I do out the work, I'm not simplifying it. And so if you're not simplifying it and they are, your answers may not always match up. So just something to keep in mind. Inverse trig is due on Wednesday, and then we're going to have implicit differentiation due at the end of the week. So on Wednesday and Friday this week, we're going to have our final type of derivative stuff, which is called implicit differentiation. And we'll see that on Wednesday and Friday due at the end of the week. Okay. So, I'm gonna give it another minute here if anybody wants to throw out any more questions. So any other questions from anybody? So exam info. So we're gonna finish chapter 2 this week. So this is the end of 2.6. Wednesday, Friday, we're gonna do 2.7. And then the exam will open up on Sunday. So I suppose if anybody wanted it earlier than that, I could open it up for them. But it'll be defaulted to open up at midnight Saturday night or early Sunday morning, and it will go through. So it'll be open from Sunday that early morning all the way through Sunday night the next week. So Sunday, so if I put some dates on this, it'll open up the morning of the 12th, and then it will close Sunday the 19th at 11:59 p.m. And so somewhere in there, you have to find 2 hours to sit down and take the exam. So once you start the exam, a 2-hour timer will start. And you have to finish the exam within that 2 hours. So as soon as you start, you have 2 hours to finish it, and you can take it anytime during the week. So there's not going to be a set time that everybody takes it. So then that's when it will open. So are there other exam questions that we wanted to? It's on WebWork, yeah. So it'll open up on WebWork. I haven't assigned it to anybody yet. I'm about 90% done with it. So I'm going to work on it here the next couple days, and then we'll open it up. Other questions? Thanks, Caleb. I heard. All right. All right. I'm going to call it here. Thanks, everybody. I'll see you all. I'll see you all on Wednesday. Have a great one. I hope you have a nice day, too. Thank you.